Doc.
Okay, we have our final speaker, who's Dr. Ji-Young Kim. He's a principal researcher with Daewoo E&C in Korea, and his interests are wind tunnel studies for tall and large span structures. He develops evaluation methods of design wind loads and wind-induced responses, and evaluations of serviceability for accelerations in buildings, and gets involved with full-scale measurements or field measurements, and also develops a damage evaluation method using artificial intelligence, and gets involved with finite element modeling using field data, and has developed a structural health monitoring system for tall buildings. So you can see we have a very knowledgeable speaker here, and I look forward to hearing what he has to say.
Good afternoon, everyone. I'm Ji-Young Kim, working at Daewoo Engineering and Construction Company. It's my honor to present my work in front of you, especially chairs Dr. Owen and Dr. Denun. Thank you. Today, I'm going to talk about some field measurement results and their contribution to the structural engineering. Nowadays, the construction industry is going down. It is mainly because of the economic recessions, global economic recessions. Also, the construction cost is increased due to the shortage of the natural resources. So, this is my boss. Always told me that, push me that to do something for surviving. And then this is me. I'm always squeezed and pressurized due to my boss. Anyway, as a wind engineer, I tried to find out some ways to reduce the wind load by checking the design wind velocities and the procedure of wind tunnel test and an evaluation method of the wind load and wind-induced responses. So as a result of such an effort, I developed some wind evaluation method, new method, and then some wind-induced response evaluation method. But there is still some problems exist. Actually, in evaluation of wind-induced effect, we have to use the structural engineers' data, such as the dynamic properties. Actually, in the evaluations of the wind-induced responses and wind load, the measured wind forces are combined with the dynamic properties, structural informations provided by the structural engineers. However, we found that the dynamic properties estimated by the FE models is quite different with the actual dynamic properties of buildings. So, such an inaccurate structural data could make some under or overestimations of wind effect. Also, this lead to the increase of the construction cost or the deteriorations of the construction quality, the building's quality. So we determined to propose a procedure to make FE models for estimating the accurate natural frequencies and mode shape. So firstly, we perform a field measurement for our chosen buildings, and then we evaluated the dynamic properties using the measured data, and then we calibrated the FE models of the chosen buildings based on the measured dynamic properties and proposed some procedures to making the FE models. These are the chosen buildings. The first three were almost constructed when the field measurement were performed. So we proposed a procedure to make FE models using these buildings, and then using these buildings, we verified the proposed FE modeling procedures. Before the construction, we predicted the natural frequencies and mode shapes, and then the predicted result was compared with the measured dynamic properties after constructions. And these buildings are case of the coupled tall buildings, and this is typical types of apartment building in Korea, and this is a case of large span loops. The overall height is about 110 and 140. We installed the accelerometers and anemometers to measure the acceleration data corresponding to the wind velocities. Also, for the data synchronizations and wireless data transmissions, we use GPS antennas and the wireless RAN system. We use a total 24 accelerometers on the building. 3 of them were installed on each floors to measure the translational and the torsional mode. Also, the accelerometers, except on the reference floor, moved from floor to floor to measure the overall mode shapes of it. Based on using the measured acceleration data, we evaluated the actual dynamic properties, and then based on the measured dynamic properties, we calibrated the FE model to match the analyzed dynamic properties to the measured ones. So, for the building 1 and building 3, the FE models were calibrated by considering these factors. Actually, the floor slabs are modeled in the FE model using diaphragms. But however, the fracture rigidity of the floor slabs should be considered in the FE model because they contribute to the lateral stiffness of the overall buildings. Also, the increase of elastic modulus of in situ concrete and non-structures were considered in the FE model for the calibrations. Actually, generally, the elastic the compressive strength of the in situ concrete is much a little higher than the specified one, because of the concrete quality controls. Also, this leads to the increase of the elastic modulus of the concrete. And then the non-structural walls are generally neglected in the FE models because they are just a non-structural element. But however, the overall stiffness, their stiffness considerably contribute to the overall stiffness of the building. So they should be considered in the FE model to get a right, accurate dynamic properties. So these factors are considered using the currently used provisions. Before the calibrations, there is the analyzed natural frequency is much less than the measured one. These discrepancies in natural frequencies makes overestimations of wind effect. However, after the calibrations, the discrepancies was reduced to the within 5%. This could make 5% savings in structural materials used. To demonstrate the importance of the accurate FE models, the wind tunnel test results were compared with the measured acceleration data as shown in this graphs. The pressure data were measured for these buildings and then converted to the wind pulses, and then the acceleration responses were calculated using the time history analysis. As shown in this figure, the accelerations derived using the original FE model is quite larger than the measured one. Therefore, this implies that the structural cost might be increased due to the overestimated wind effect. To test the reliability of the FE model calibration method, the natural frequencies were predicted for the building 4 before the construction, and the result was compared with the dynamic natural frequencies measured after the constructions. As shown in this table, the natural frequencies of this building could be successfully predicted using the calibrated models. So this means that our proposed procedures could be could be properly used in practical analysis works. Also, this is a case of a coupled tower. Nowadays, two or three towers are usually connected using the sky bridges or podiums. As shown in this figure, they are usually modeled independently because they are regarded as disconnected using this expansion joint. However, as shown in this mode shapes, they show some coupled responses. Therefore, the coupled effect should be considered in the FE model. So therefore, both of the buildings were modeled in one full FE model, and then the expansion joint is modeled using the link element. The stiffness of the link element is assumed according to the material properties of the expansion joint. As shown in this table, after the calibration, we can also properly estimate the natural frequencies. This is a building. This is a building of a typical type of building in Korea. The apartment buildings usually consist of the shear walls, only shear walls. Therefore, between the shear walls, there is some balcony parapet constructed using reinforced concrete. So this kind of balconies influence the overall stiffness considerably. So after considering this balcony parapet in the FE model, we could get more accurate natural frequencies as shown in these tables. Also, a field measurement was performed for large span loops. As shown in this figure, the loop trusses were fabricated on a temporary shoring structures, and then the mast was linked to the rear of the loop trusses, and then the stay cables are tied, and then the stay cables were pre-stressed. After that, the shoring structures were removed. These procedures of the construction was considered in the model makings, and using this FE model, so we can get accurate natural frequencies compared with the measurement result. Also, the wind tunnel test result was compared with the measured accelerations as shown in this figure. So the pressures on the loops was measured concurrently, and then we performed the time history analysis using the measured pressures. Also, the measured damping ratios are used for the dynamic analysis. In the dynamic analysis, the aided mass effects also considered for the evaluation of the wind-induced responses. The fluid, generally, fluid near the surface could act as an additional mass of it. So, Owen and Minami proposed an expression for the added mass. After the after considering the added mass for the evaluation of wind-induced responses, we could get more accurate result, as shown in these figures. So from these comparisons and calibrations, I think that we should pay more attention to the FE modeling to get a more accurate result from the wind tunnel test. We should consider the in-situ material properties, non-structural elements, coupling pattern, and so on. Also, we have to perform more studies about the dampings and aerodynamic effect using field measurement. Such and more attention to the FE models, I think, contribute to the safe construction material as shown in this amount. And then, on the other hand, also we could make some CO2 reduction as shown like this. So, I think that I can make more accurate FE models. I can save my company, and then I can save my Earth. So thank you. I'm still serious because my boss always said that I'm now still hungry. Thank you.
Okay, we have time for a few questions. Have any questions from the floor? Professor Tamura.
Interesting presentation. I enjoyed, and you are already doing some challenging trial. So I have a question about the natural frequency you adjusted. The measurement was made in the very low amplitude level.
Sorry?
So I think the measured value of the natural frequency is based on the low amplitude level.
Yes, yes.
So the contribution of the secondary member or non-load bearing members significant in that case. But in the high amplitude level, such an effect is reduced. That suggests the reduction of the natural frequency.
Yes.
In the case of high amplitude level. So if you adjust the FE model based on the full-scale data in low amplitude level, it becomes dangerous.
Yes, I see.
In the case of safety level of the, but habitability level may be possible, but
yes.
Safety level it becomes dangerous, I guess. So
yes, yes, I think yes, I understand. I agree with you. Actually, the structural designer performed according to some procedures. Firstly, the dimensions of the walls, shear walls, and column size are determined according to the serviceability levels. In serviceability level, we generally some criteria, the lateral drift criteria, such as 500 over H. 500 over H. This kind of criteria makes the determine the structure size of the building. After that, the reinforcement of the concrete members are determined based on the limit state design. So I think it could be used
like
for the serviceability.
More information about that. In Japan, the natural frequency, measured natural frequency is almost 20% higher than the design stage.
Yes.
Both for concrete structure and steel structure.
Yes.
And this March, we measured the high amplitude vibration due to earthquake. The natural frequency almost similar to the design value.
Yes.
So the 20% increase in the full scale result in the low amplitude level is only for habitability.
Yes.
But
Yeah,
I think
yes.
so for the safety level, I think you should change the natural frequency
yes,
from the
yeah.
measured value.
Yes, for the safety designs, we changed the natural frequencies, as you said, 20% lower than the serviceability level. So this is the procedures of the structural analysis, structural designs. So I'm agree with you, and then I will try to find out some criteria for the natural frequencies and in ultimate states.
Do we have any more questions from the floor?
I think with that we can thank Dr. Kim for his fascinating presentation. So I think if we were to sum up that session on wind engineering, there's been a remarkable degree of consistency. We've heard two very strong stories. One is for the importance of doing field measurements to improve the accuracy of our predictions and the reliability of future design. The other story we've heard is the importance of tweaking the architecture to get the loads down as far as possible, and the importance of doing that early in the design phase. And I think it's been very nice to hear those consistency of stories through this session. Obviously, many of you who've worked with wind tunnels have realized that you don't always get a consistent story from them. So this is where I go into slight sales pitch mode, in that within the wind engineering working group of the CTBUH, we've been preparing a guideline for users, for clients, for engineers, for architects to understand a little bit more about the process of wind engineering, wind tunnel testing, and what to ask for. So if you would like to learn more about that, Peter is going to be speaking about that in the session after the coffee break on design guides, which will be in room 103, and you can learn what we've been doing on that. So with that, let's just wrap up the session and thank all our speakers again for some very fascinating presentations.